All right, practice questions. First set, we're on page 250, and these are with gravitational potential energy. So 27 says a frame picture is to be hung on the wall and is lifted through a distance of 2 meters. So that's your delta H, 2 meters. If the picture has a mass of 4.45 kilograms, so 4.45 kgs, calculate its gravitational potential energy with respect to the ground. So delta Eg if you want, so mg delta H, the ground would be 0, so the final gravitational potential energy or the change will be the same. So you can put a delta or not, it'll be the same thing. 4.45 kilograms, don't forget the 9.81, it's mgh, meters per second squared, times 2 meters. And when you do this, you should get an EG of 87.31 joules. Number 29. I skipped 28 on purpose because it's a little weird. How high would you have to raise a 0.3 kilogram book? So mass is 0.3 kilograms. And so you're looking for delta H or HF, assuming HI is 0. In order to give it 24 joules of gravitational potential energy. So you want your EG to be, I said 24, but I think it's 12 joules, or your delta EG if you're using delta H. So since I used delta on the last one, I won't on this one. So it would be mgh, okay, so delta final, I know I just said I wasn't going to, but this would go to 0. Like, that's why I'm saying it's okay to not have the delta in there. Okay, so you're looking for your final height. So delta Eg divided by mg. So 12 joules divided by 0.3 kilograms times 9.81 meters per second squared. And when you do this, you should get an HF to be 4.08 meters. Okay? That's how high you would have to raise it. All right, so then flip over a couple of pages to 254. Number 30 says a student lifts her 2.2 kilogram, so mass, 2.2 kilogram, pile of textbooks into her locker where they rest, from where they rested on the ground. She does 25 joules of work, so that's your EG. Calculate the height, which is that the student must lift the books. So again, delta Eg is equal to mg delta H, so you're looking for the change in height. So delta Eg over mg. So 25 joules divided by 2.2 kilograms times 9.81 meters per second squared. You should get a change in height to be 1.158 meters. Number 31 says a 46 kilogram child cycles up a large hill to a point that's a vertical distance of 5.25 meters from the starting point. So delta H, 5.25 meters. Find the change in the child's gravitational potential energy. Delta Eg is equal to mg delta H is equal to 46 kilograms times 9.81 meters per second squared times 5.25 meters. When you do this, you should get a change in gravitational energy to be 2,369.12 joules. That is part A of 31. Part B says, what's the amount of work done by the child? Well, remember, work done is equal to change in energy. So you already have the answer. It's 369.12 joules. Okay, so work done, change in energy, same thing, no further work required. Number 32, a 2.5 kilogram pendulum is raised vertically 65.2 centimeters. 65.2 centimeters, which of course is 0.652 meters. Find the gravitational potential energy of the pendulum. Okay, so the change in EG is equal to mg delta H. Change in EG is equal to 2.5 kilograms, 9.81 meters per second squared, 0.652 meters. And the change in will be equal to the final because the initial again is 0. I haven't been saying that in all these questions, but it's true. And you get 15.99 joules. Number 33. Says a roller coaster train lifts its passengers up vertically through a height of 39.4 meters. So delta H is 39.4 meters. From its starting position. Find the change in gravitational potential energy if the mass is 3.9 times 10 to the 3. 3.9 times 10 to the 3 kilograms. So EG is equal to mg delta H. 3.9 times 10 to the 3 kgs, 9.81 meters per second squared, 39.4 meters. You should get an EG of 1.507 times 10 to the 6 joules. All right, so hopefully you got a hang of the gravitational potential energy. The next set is over on page 258. Question number 35, and these are with Hooke's law. So it says a spring scale is marked from 0 to 50. So imagine a spring scale. Okay, and up here is 0 newtons and down here is 50 newtons. So that if you hang something off it, it'll stretch the spring. Okay, and it says that this whole thing is 9.5 centimeters long, which means if you put 50 newtons on it, you're going to stretch the spring a distance x of 9.5 centimeters. So it wants to know what's the spring constant. So we know F equals kx. So K equals F over x. So 50 newtons stretches it 9.5 centimeters or 0.095 meters. So K will end up being 526.3 newtons per meter. Number 36 says a slingshot has an elastic cord tied. It has a spring constant, so our K is 1.1 times 10 to the 3 newtons per meter. A force of 4.5, so F is 455, sorry, no point in there, 455 newtons, and it wants to know how far. So F equals kx, x equals F over k. So 455 newtons divided by 1.1 times 10 to the 3rd newtons per meter. And you should get an x of 0. I'm going to run out of time again, 141 meters. Part B says what's the restoring force? It's going to be exactly the same thing, just in the opposite direction, 455. Number 37. Spring constant in a typical Hooke's law apparatus has a force constant. So K, we're going to run out of time. K is 1.5 newtons per meter. And it says maximum extension of 10 centimeters. So X is 10 centimeters. And it wants to know what must be the mass. So what it's saying here, and this is where we're going to run out of time. So here's my spring hanging from the ceiling. I'm going to hang a mass off of it.